Just 5 meters long, a single LED strip can contain hundreds of pixels, with each pixel capable of producing more than 16 million colors, enough to transform a thin circuit strip into a vivid light show. But to make hundreds of light points operate uniformly, change colors accurately, and display continuous effects, factories must mount countless microscopic components onto a flexible circuit board only a few millimeters wide. From printing copper traces and placing high-speed chips to soldering components, applying protective coatings, and testing every single LED, even the smallest error can cause an entire section to flicker, display the wrong color, or stop working altogether. So how are electronic chips smaller than a fingertip assembled into a flexible strip of light capable of bending, running dynamic effects, and producing millions of colors? Let's explore the complete LED strip manufacturing process inside the factory. Few people would imagine that an LED strip only a few millimeters wide stands behind a lighting industry valued at approximately $107 billion in 2025. From the giant billboards of Tokyo, Seoul, and Las Vegas to automobiles, stages, factories, and smart cities, these tiny points of light are filling the modern world with color. But before an LED strip only a few meters long could help create glowing boulevards, breathtaking stages, and entire cities illuminated throughout the night, scientists first had to conquer a color once considered nearly impossible: blue. While red and green LEDs had already appeared much earlier, blue LEDs left researchers struggling for decades because gallium nitride was extremely difficult to manufacture. Only after this barrier was finally broken could the RGB color system be completed, efficient white light become possible, and the LED revolution truly begin. The breakthrough was so significant that it earned the 2014 Nobel Prize in Physics for Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura. Few people realize that behind these tiny LED strips lies semiconductor technology, one of the most strategic technologies in the world, with major powers investing hundreds of billions of dollars to master it because it forms the foundation of computers, smartphones, automobiles, and nearly every part of the modern world. The design process begins by defining the color, brightness, voltage, and operating environment of the LED strip. From there, engineers calculate the chip structure, the composition of the semiconductor materials, and the size of the light-emitting region. Even an extremely small change in the InGaN layer can shift the wavelength and alter the color of the emitted light. At the same time, the flexible circuit board is laid out to distribute electrical current evenly to every chip. LED spacing, copper trace width, and resistor placement must be carefully balanced to control brightness, heat generation, and service life. Only after the electrical, thermal, and optical performance has been simulated is the final design converted into manufacturing data. Once the design is complete, sapphire wafers are loaded into an MOCVD reaction chamber and heated to approximately 1,832 degrees Fahrenheit. At this temperature, gas compounds containing gallium, indium, and nitrogen decompose, allowing individual atoms to settle onto the wafer surface and form extremely thin semiconductor crystal layers. This process is similar to building an LED chip one layer at a time: a lower conductive layer, a light-emitting region in the middle, and an upper conductive layer. When an electric current passes through the chip, the light-emitting region produces photons. Most remarkably, changing even a tiny amount of indium in the InGaN layer can shift the emitted light from blue to green. Throughout the entire process, temperature, pressure, and gas flow must be controlled with extreme precision. Even the slightest deviation can cause the color and brightness of thousands of chips across the same wafer to become uneven. Once the semiconductor layers have been grown, the wafer is still nothing more than a flat surface. To transform it into thousands of individual LED chips, the factory uses photolithography, a technique similar to printing an extremely tiny pattern onto the wafer with light. First, a light-sensitive material called photoresist is deposited onto the wafer, which is then spun at several thousand revolutions per minute. Centrifugal force spreads the liquid into a thin, uniform coating before the wafer is baked at approximately 194 to 230 degrees Fahrenheit. Next, ultraviolet light is projected through a photomask containing the chip pattern. The exposed regions change their properties and are washed away by a developing solution, revealing the semiconductor areas that must be processed. An etching machine then removes material from these locations, forming steps within the chip structure and opening access to the conductive layers below. The coating, exposure, and etching process must be repeated several times. Each cycle adds only a small part of the final structure, but once complete, the entire wafer has been divided into thousands of nearly identical LED structures with extremely high precision. Once the entire chip structure has been completed, a single wafer may contain tens of thousands of identical LED chips. However, they are still connected on the same sapphire substrate and cannot yet be used individually. To separate them, the wafer is loaded into a cutting machine equipped with an ultra-thin diamond blade or a highly precise laser. The system cuts along predefined lines between the chips with an accuracy of only a few micrometers. Even a slight deviation can crack the chip or cut into the light-emitting region, rendering the entire device unusable. Once the cutting process is complete, tens of thousands of individual LED chips have been produced. Each chip measures only a few hundred micrometers to around 1 millimeter across. Yet these microscopic components will become the light sources inside the bulbs, displays, and LED strips we use every day. At this stage, the LED chips are still nothing more than microscopic pieces of semiconductor material. To function, each chip must be placed inside an LED package only a few millimeters long, which already contains electrodes, a reflective cavity, and a heat-conducting surface. These packages are typically made from heat-resistant engineering plastic combined with metal, while high-power LEDs may use ceramic substrates for better heat dissipation. Before the chip is mounted, the machine deposits an extremely small amount of silver adhesive or bonding material at the center of the package. This layer secures the chip while also conducting electricity and transferring heat downward. Too little adhesive may cause the chip to detach, while too much can overflow onto the electrodes. Immediately afterward, the die bonder begins operating. A high-resolution camera precisely identifies the position of each chip on the wafer. A microscopic vacuum nozzle then lifts the chips one by one and places each of them at the exact center of a prepared LED package. The entire process happens almost instantly, with a positioning error of only around 10 to 20 micrometers, less than 1/5 the diameter of a human hair. Remarkably, the system's speed is barely affected by the microscopic size of the chips. Modern die bonding machines can mount between 15,000 and more than 30,000 chips per hour, equivalent to roughly 4 to 8 chips every second, while maintaining near-perfect accuracy. A misalignment of only a few dozen micrometers can cause the wire bonding process in the next stage to fail or reduce the LED's ability to dissipate heat, forcing the entire component to be rejected. Within a very short time, tens of thousands of semiconductor chips have been positioned accurately inside individual LED packages, ready for the next stage, connecting each light-emitting chip with gold wires thinner than a human hair. Once the chip has been secured to the package, it still cannot receive electrical current. At this stage, a wire bonding machine uses an ultra-fine gold wire to connect the electrodes on the chip to the two metal terminals of the LED package. The gold wire has a purity of approximately 99.99% and a diameter of only 18 to 25 micrometers, making it several times thinner than a human hair. The machine's bonding tool lowers onto the chip and combines heat, pressure, and ultrasonic vibration to attach the end of the wire firmly to the electrode. The wire is then drawn into a small arch before its other end is bonded to the package. The entire operation takes only a fraction of a second, but the required precision is extremely high. A single weak bond, an overly tight wire, or an incorrect loop height can cause the LED to flicker, shorten its service life, or stop emitting light altogether. After the gold wire bonding and initial inspection are complete, the LED trays are transferred to the phosphor coating area, the stage that determines the product's final light color. Here, phosphor powder is weighed using equipment with a precision of up to 0.0001 gram. Depending on the required color temperature, engineers blend several types of phosphor in carefully calculated proportions, then place the mixture inside a high-speed mixer to disperse it evenly throughout an epoxy solution. The mixture is then loaded into the cylinder of a phosphor dispensing machine. Microscopic needles deposit an almost identical amount of the solution onto each chip, with volumes controlled down to millionths of a liter. Even the slightest variation can cause the LED to appear bluish, yellowish, or noticeably different from the rest of the batch. Interestingly, a white LED does not actually emit white light from the beginning. Most chips produce blue light, while the phosphor layer above converts part of that light into yellow. These two colors then blend together, creating the white light perceived by the human eye. Once the phosphor layer is complete, the SMD LEDs are transferred to the SMT production line for mounting onto the flexible circuit strip. First, the FPCB roll passes through a solder paste printer, where a thin steel stencil helps deposit a nearly identical amount of material onto each copper pad. The paste temporarily holds the components in place and later forms the electrical connections during heating. Next, the pick-and-place machine uses cameras to verify polarity before positioning each LED, resistor, and control chip in the correct location. Component spacing must remain precise, because a single misaligned or reversed LED can create a dark spot, display the wrong color, or cause an entire section of the circuit to stop working. Finally, the circuit strip travels through a reflow oven divided into several controlled temperature zones. The solder paste melts at more than 460 degrees Fahrenheit, then solidifies to lock the LED terminals onto the copper traces without warping the FPCB or damaging the phosphor layer. Within only a few minutes, hundreds of separate components are transformed into a complete LED strip. After leaving the reflow oven, the LED strip is not packaged immediately. It must first undergo electrical and optical inspection. The system powers the entire strip, while automated cameras scan each point of light to detect dead LEDs, incorrect colors, uneven brightness, or misplaced components. At the same time, testing equipment measures voltage, current, and power consumption to ensure that the strip operates according to its original design. Even a tiny defect in a solder joint can cause an LED to flicker when the strip is bent. For this reason, many factories bend or roll the strip while it remains powered. This test helps reveal weak solder joints and microscopic cracks in the flexible circuit that are difficult to detect with the naked eye. Only strips that pass every inspection are transferred to the protective coating and packaging stages. Approved strips are then coated with silicone or polyurethane. This transparent material forms a thin protective shield that helps resist moisture and dust while reducing damage when the strip is rolled or installed in confined spaces. For outdoor products, the entire circuit may be sealed inside a silicone tube to provide greater water resistance. Once the protective layer has cured, the LED strip is cut to standard lengths, fitted with connectors, rolled into individual reels, and inspected one final time before packaging. After passing the final inspection, the LED strip is cut precisely at the designated points on the circuit, then fitted with power wires or connectors according to the product model. A layer of double-sided adhesive may also be applied to the back, allowing users to mount the strip directly onto walls, cabinets, or decorative frames. Next, the LED strip is wound evenly around a plastic reel. The machine must maintain the correct tension because winding it too tightly can bend the flexible circuit, crack the copper traces, or place excessive stress on the solder joints. Each reel is then powered on once more for a quick full-length inspection before being placed inside an anti-static bag or sealed package. The outer packaging is printed with specifications such as voltage, power consumption, color temperature, length, and water resistance rating. The finished cartons are scanned, stacked onto pallets, and transferred to the warehouse. There they are organized by production batch and stored in a dry environment away from excessive heat and humidity before being distributed to retailers, construction sites, and assembly plants around the world. From semiconductor layers only a few micrometers thick to hundreds of components assembled with near-perfect precision, an LED strip only a few millimeters wide is the result of combining materials science, optics, electronics, and automation. Behind every finished reel are dozens of manufacturing stages and countless rigorous inspections, all working together to create a durable light source capable of operating for tens of thousands of hours. Today, billions of LED chips are produced every year, illuminating everything from homes, automobiles, and factories to skyscrapers, stadiums, and smart cities around the world. A technology that once took scientists decades to master has now become an essential part of modern life. If you enjoy discovering how everyday products are made inside the world's most advanced factories, please like, subscribe, and turn on notifications so you never miss the next video from Factron Process. Thank you for watching, and we will see you again on the next journey of discovery.